So, hi sir. So, my today I'm going to present my pitch on smart digital thermometer. So, basically, temperature monitoring. It is one of the most basic but important health measurements. So, and this particular thermometer it focuses on creating and what a smart, accurate, and an efficient thermometer system basically, which provides with quick readings, user alerts, and also reliable performance. So yeah, so let me move on to my problem statement. So basically, why do we need smart thermometers, and what is the motivation behind this actually, and what are the challenges behind the traditional thermometers? So all this is discussed here. So basically, we know that traditional thermometers have various limitations which are present. So there are many slow responses which are there, and due to this there is a delayed diagnosis. So manual reading also can lead to human errors, especially in busy medical areas and environments. So these can reduce the efficiency of the overall system. So thereby there is a need for a smarter solution that can provide for an accurate and also a fast continuous temperature measurement. So basically, let me move on to the project objectives. So we can see the goal and key targets of the project. So let me explain some of the objectives of my project, which include the first is the main objective, which is to design and implement a smart digital thermometer system that can continuously monitor the temperature in real time. So the second objective is basically to provide a digital display so that the users can easily read the temperatures without any ambiguity. And also another important is to include a fever alert system basically, which is done using a buzzer, so that the abnormal temperature conditions are immediately brought to users' attention. So let me move on to the system specification, the purpose and the inputs and the outputs. So the first thing is the purpose of the system. Basically, it is to continuously sense and display the temperature with high accuracy and reliability. So the thermometer is basically designed to work with sensors such as LM35, which provide temperature readings either in analog form or also in digital form. So the main inputs of the system, if I have to say, we know that it is nothing but the sensor data and the power supply and also the user commands, which include turning the device on and off and etc. So we know output also, we know actually it is nothing but the digital display showing the temperature reading, the status of the what do you call the messages and the stable measurement and the error condition and also the buzzer alerts. So next the requirements. So let us move on to the functional and the non-functional requirements of the system. So basically, what are the functional requirements? It includes the continuous temperature management and measurement, and which includes real-time display updates also, and Celsius to Fahrenheit conversion. So all these things are present along with calibration features. Next, if I have to go the non-functional side, first thing, accuracy must be perfect. Second thing, reliability should be there. Third thing, resistant to sensor noise, energy efficient. So all these things are the requirements of the system. Next is the overall system overview and the architecture diagram. So this is the block basic architecture of the system. So if I have to tell you, the block diagram is also present. So yeah, next thing. Basically, if I have to tell about the system architecture, it first senses the surrounding or the body temperature and it converts it into an electric signal. Then an LM35 sensor is used. Then the signal passes through a signal conditioning and analog to digital conversion. Then the microcontroller processes the data, applies the filtering and calibration, updates the display, and then the threshold is updated. And finally, due to the threshold, alerts are coming. So this is the overall flow which I've explained. Next, key features. So basically, in key features, if I have to say, some of the standard key features of this thermometer system include the digital filtering, continuous temperature sensing, flexibilities, threshold alerts, and also low power sleep functionalities, which helps to improve the battery lives and makes the systems more efficient for longer use also. Next one are the hardware components. So we already the hardware design includes multiple components. First thing, the LM35 or DS18B20 sensors. Next thing, microcontroller, which is the brain. Next is the LCD display. So other than that, we have a buzzer also. So to generate the alerts, push buttons can also be used for switching units or resetting values also. Next one, software task flow. So this is the software task, how the processes go. So basically, this is designed in a modular and text task based manner actually. So the first task is basically the sensor reading, where the raw temperature is collected, and then after the collection, the temperature is processed. Then the processing is done and converted, and then after the processing, it goes to the filtering, and the filtering task is done. Then finally, you go to the filtering and alert checking layer, and then the display layer. So all these the tasks. So as you can see it in the particular diagram, processing, reading, alert check, display, in user in output, input. So everything is present. So this is the software task flow. Next one is the subsystems involved in the system. So there are basically three core subsystems. As I told you, first is the temperature sensing system, which detects the physical temperature and using the sensor, and it converts it into an electric signal. So this is the subsystem involved of the three core system. First thing is this. Second one is the control and processing subsystem. So where the microcontroller reads the data, performs the calculations, and applies the filtering. Thirdly, lastly, the user interface, where the user interact and the LCD display is there, and they can view the temperature readings and interact with the device. So these are the three subsystems. So let us now move on to some of the models. So first, if I have to say, it is the Petinet model. So as you can see, I have attached my diagram also from my particular DA which I have submitted. So this is the Petronet model. So it represents the full operational flow of the smart thermometer system, which starts with the initialization, then it moves to the sampling state, then it moves on to the next state, which is the raw data processing state, then the threshold checking, exceeding the threshold, then it goes to alert state, and the activation of the buzzer, then finally the user interaction. So it includes for calibration requests, error handling, everything. So this is basically the flow of the Petinet model, how it occurs from starting to the end. It includes the system operations and the system behavior. Next, use case diagram. So use case diagram, as we know, it includes the use cases that are the actors also in the use cases. So the use cases are the initialization, sampling, processing, alert, calibrations. All these things are present. So along with that, who's the primary actor of the system? We have to know about that. So the primary actor is nothing but the person who's performing the major actions, such as powering the system, selecting the temperature units, and initiating calibration. So all these things. Then tasks, as I had mentioned, data processing, generating alerts, displaying results, and overall functionality. Next one, sequence diagram. So it shows the communication and the interaction flow between system components. So we have the thermometer, sensor, processor, display, alerts, so all these things present. So initially the user powers on the thermometer, then the request is gone, then the sensor sends the raw data back to the controller, which processes it and then filters it. After processing, the microcontroller would update the display, and then if the measured temperature exceeds the particular threshold, then of course the signal is sent to the buzzer to get immediately activate the fever alert command or the thing. So basically, this is how the overall interactions happen. So this is about the sequence diagram. Next, use class diagram. So it shows the overall software structure of the digital thermometer. So the sensor class, the signal conditioning class, which processes the raw signals and removes noise. Next, the controller class is present, which also acts as the main decision making class. Then the display class, which handles the showing and reading the messages and the, sorry, showing the readings basically. Then the alert system also is present. So all these classes are present. So you can see alert system, user interface, signal processing, sensor classes. Finally, testing was done. So three types. First one, the first unit testing. So test separate modules. Then integration testing, test it fully. What do you call? Communication between modules are tested by checking for others. Finally, whole system testing to check the complete thermometer behavior. So these are some of the test cases which were done, and testing validation is done. So this is basically about the testing part. So finally, I would like to say that because through my smart thermometers, you can have what great processing features, alert features, efficient design is also present, and it acts it has a good modular structure and architecture. So thank you.